Our next speaker will be Peter Decker. Peter Decker started his professional career at the semiconductor R&D department of Robert Bosch in Reutlingen. And since 2002, he is employed at Vector Informatik GmbH in Stuttgart. And there he is product manager in the area of multi-bus development for the software tools Canu and Canalizer. Many of you may know these tools, so I already worked with them and still do. At SIA, we do not stop when we finish the CAN XL data link layer specification. So we try to provide a whole ecosystem for CAN XL because only then it can be successful. And Peter is deeply involved in specifying this ecosystem and helps us with his wide knowledge. And so he is not just an expert on the data link layer, but also on the higher layer. Today, Peter will tell us about the Internet protocol concepts on CAN XL. And Peter, I'm looking forward to your talk.
Okay, thank you, Arthur, for the nice introduction. So welcome also from my side to the CAN conference. Well, CAN XL is emerging more and more, and in the past few months I read sometimes about CAN XL. Well, it's the guardian of the old world. So I was somehow amused about that, but of course when we think about Automotive Ethernet that brings IP communication and the internet into cars, well, it somehow seems to be old-fashioned. Is it really old-fashioned? Well, I'd like to talk now about how we can implement and apply IP concepts also on CAN XL. What I experienced recently is that we see a certain consolidation towards Ethernet and CAN communication in in-vehicle networks. So that means that protocols like FlexRay and MOST, so these use cases can basically also be covered by CAN XL and Ethernet. Now let's have a look on what this consolidation means for the 10 megabit domain in automotive networks. Now, Ethernet today uses bit rates between 100 megabit and 1 gigabit for use cases such as ADAS or connectivity, while for classical embedded control use cases like engine management, still CAN or CAN-FD are widely used, providing bit rates up to 5 megabits. But what about a 10 megabit domain? There are still also many use cases located in that domain. And there are two solutions available today or upcoming that could occupy that domain. One is Ethernet based, called 10BASE-10.1s, and the other solution, of course, is CAN XL. Now let's have a closer look on those use cases. As I already mentioned, you can either realize a network in the 10 megabit domain using 10BASE-T1S, or you can use CAN XL. Well, what we have to consider is how the communication is realized. And when we talk about CAN, usually we talk about a signal-based communication. That means you have signals of fixed size that are statically mapped to a CAN frame. In Automotive Ethernet, usually you work service-oriented. For that, a scalable service-oriented middleware over IP, short sum IP, is used. And here you have dynamic data structures because you have use cases like sensor fusion or streaming, and that means that the size of the data is determined at runtime of the application. And this also means that the data are not mapped anymore statically to a frame, but are serialized dynamically. Now, if CAN XL needs to cover all those use cases in the 10 megabit domain, it requires to handle service orientation which is today based on IP communication. And how this should work, I'd like to discuss in the further presentation. I will focus in this presentation on the automotive industry and on the software architecture provided by AUTOSAR. Okay, let's come back to data serialization. Well, this is one of the basic functions that's provided by a service-oriented communication. And the serialization is realized with a module called SUMIPEX that is located in the middleware layer of the AUTOSAR software stack. And this means it can also be used for CAN XL. So that's good news, because if you adapt the AUTOSAR software layer, that's done basically in the lower layers. That means data serialization is already available. Now, before I talk in more detail about service orientation on CAN XL, let me discuss a little bit service orientation in general. And the first question probably is, what is a service? Well, you can think of a service just as a container that contains event groups and methods, where an event group is just data that is cyclically transmitted, and a method is an RPC called a remote procedure call. So the advantages of service-oriented communication is that you can easily move services between different participants in the network. And this is really crucial for variant management in vehicles. And service orientation also allows you to set up the communication dynamically at runtime. And how this is done, I'd like to show now. So assume node 3, Ethernet node 3 is a service consumer and requires service 1. It does not know which participant offers the service, nor does it know the IP address of the service, neither does it know the MAC address. Now, node 1 is the service provider. It provides now the service by a service offer that's performed with the so-called SUMIP service discovery. So SD stands for service discovery. So SUMIP is more or less a protocol with two parts. So it provides a service discovery part and a communication part. And at the beginning of the communication, we provide this service discovery. Now the service is broadcasted into the network. Usually it's a multicast technically. And with the service offer, also all data that are required for the service are provided, such as the IP address and the port number of the service. So now it's possible that node 3 just subscribes, for example, to an event group or calls a method on the service provider. But before that can be started, node 3 has also to determine the MAC address, and this is done by an address resolution protocol. It's also possible that this process works in a semi-dynamical way. In that case, the IP and MAC addresses are statically mapped. That means you still can move the services between participants, but you cannot anymore easily change IP and MAC addresses. But what you gain is that you save the address resolution protocol, and that makes, for example, the system startup faster. And both processes can be found in today's in-vehicle networks. Okay, now let's finally talk about service orientation on CAN XL. Now, when we talk about IP concepts and service orientation on CAN XL, you usually can assume that CAN XL will be connected to an Ethernet network, to an Ethernet backbone, or maybe to a zone ECU. And of course, in that case, it is required that the data are routed from the backbone network to the CAN XL network. And this can be done on different layers, from the application layer and also down to the data link layer. And that's where I like to start now the discussion, connecting a CAN XL network on layer 2 to an Ethernet network. And well, how can we do this? Well, the simple question is we use a gateway. That will always work. But it would also be convenient if you just could use a standard Ethernet switch. And in that case, I'd like to introduce something I like to call CAN XL PHY. I'd like to do that only for didactical reasons. So just to emphasize that this is not a simple transceiver device, not just an analog device, but a device that also needs to implement a CAN XL controller logic. From implementation point of view, of course, you can implement that differently. So you can also have a specialized CAN XL port. But as I already mentioned, from didactical reasons, I'd like to talk about a CAN XL PHY that's just connected to a standard Ethernet switch. So now we're coming back to routing the data. And this, of course, requires that we embed an entire Ethernet frame into the CAN XL frame. That's possible. Payload of CAN XL is large enough, as we already learned in this CAN conference. The second thing is that each CAN XL node requires to provide a virtual MAC address. That means more or less the CAN XL network is a kind of virtual Ethernet network. Let's come back to the CAN XL PHY. Well, actually, only one CAN XL PHY would be required that is attached to the Ethernet switch. On the CAN XL nodes, it's still sufficient to use common transceivers. Now, the main function, or a basic function of that CAN XL PHY, is that it copies and extracts the Ethernet frame into and from an CAN XL frame. Let's see how this looks now for the AUTOSAR stack that you require in the CAN XL nodes. What do we have to change here? And the answer is we just have to change a real low layer called the interface layer. So the interface layer more or less needs to implement CAN and Ethernet behavior. So CAN behavior towards the CAN driver, Ethernet behavior towards the higher layers. And that means the higher layers remain just the same like in an Ethernet stack. Now let's see how the communication would look like. So we have here an Ethernet node that is now transmitting into the CAN XL network. So as mentioned, in that case, we require a MAC address because an Ethernet switch does just know about MAC addresses, and those MAC addresses are configured in the port where other nodes or networks are connected to. So the next thing is, of course, we require CAN IDs, at least one for each CAN participant, to set up our CAN communication. And it would also be good if we had possibilities to filter the traffic in the CAN XL network, because still CAN XL uses a shared medium. That means all messages, all frames are broadcasted on the network. And so it would be good if you could filter out traffic that is not important for some of the nodes to just save interrupt latencies. And this, for example, could be done by just filtering on the embedded MAC address. What's really good about this approach is that all the protocols that are embedded in the Ethernet frame can just be used as is. We've just seen that earlier when we discussed the AUTOSAR stack for that method, embedding an Ethernet frame into CAN XL. Okay, now let's have a look what can we do instead of routing the entire Ethernet frame to CAN XL. And the other possibility could be that we just route the IP traffic to CAN XL. In that case, of course, we really need to use a gateway. and embed the IP packet into the CAN XL frame. In that case, of course, we have to provide more changes to the AUTOSAR layer. Not only the interface layer needs to be adapted, but also the TCP IP stack, especially those protocols that are really tightly bound today to Ethernet communication. Again, let's see how the communication looks like. So now the gateway extracts and copies the IP packet from the Ethernet frame to the CAN XL frame and vice versa. Again, of course, we need CAN IDs, at least one for each participant, for the CAN communication, for the network access. And also here, filtering would be a good idea. That could be done, for example, on the embedded IP address. What's also pretty good is that also here all protocols that are embedded and are above IP communication can just be used like on an Ethernet network. That means service orientation can be applied in that way also very smoothly. Now, after I showed how service orientation could be used using IP communication, I'd like to introduce an idea that we call SUMCAN. It's just an idea from several vector colleagues, and that's what I'd like to talk now. What we previously have seen is that you require a TCP IP stack for the entire service-oriented communication. But would it be possible to save that TCP IP stack? And the answer is yes, probably this could work. And I'd like to show you now how this could happen. So in that case, we need to introduce a new module I call the SUMCAN module. And this module more or less provides the same functionality like the socket adapter module in an Ethernet stack. Now the crucial part is how service discovery works on CAN XL. And service discovery, and generally some IP is a little bit spread throughout the AUTOSAR stack, and we need to take a look on how the SUM IP and the SUM IP SD header are serialized. So the first part of a SUM IP header is serialized by the SUM IP XF serialization module. The second part is serialized when we talk about an Ethernet stack from the socket adapter. Now when we talk about SUMCAN, it's serialized from the SUMCAN module. All the data required for service discovery is serialized by the service discovery module. And we can see that there are already all the data types available that we need to set up a service-oriented communication. So actually we don't really require for setting up a dynamic service-oriented communication and TCP IP stack. So here, for example, we have the type field. When we talk about Ethernet, this type field holds the IP protocol that is used, so IPv4 or v6. In the case of SUMCAN, that we just have to introduce a new type called, for example, CAN XL. Then we need to address the service. That's what I've shown earlier. For that, we require an IP address and a port number. And now for CAN XL, for example, this could be an ID, a CAN ID that just identifies the service. An even better idea is to separate the concerns, and so that we just use the CAN ID for network access is to introduce a node address. My thinking at the moment is we don't require a port, but if required, still something that is semantically a port could also be introduced for SUMCAN. Let's go back and talk a little bit about routing, because this is becoming a little bit more complex. especially in the case of the service discovery, we need to deserialize the entire some IP message in the application and serialize it again with the help of the some CAN module. When the some IP communication is going on, the situation is a little bit better, because in that case, we just can use the AutoSAR PDU and route them through the AutoSAR PDU router module. Okay, now let's talk a little bit about addressing and filtering for some CAN. Usually service-oriented communication is more or less a peer-to-peer communication where participant-based addressing is used. So in the case of some IP, we have the IP and the MAC address. Now we require something similar for some CAN, and so I'd like to introduce that each node provides a node address, and CAN XL comes with a new field called the acceptance field, and that can be used to hold the node address, and then we have also the possibility for an early filtering. Of course, we require in that case also a multicast and broadcast address for the service offering. And it would be also convenient if we introduce a new data type for the data type, service data type field in CAN XL called some CAN. So it is possible for nodes that are maybe not participating in the service-oriented communication to already filter on that field. Well, and the best news at the end, the acceptance field can not only be used for some CAN, it can generally be used for early filtering. So this can also be applied for embedded Ethernet communication or embedded IP communication by just mapping at least a part of the MAC or IP address to the acceptance field. Okay, let me summarize what I showed you today. So the automotive 10 megabit domain requires service-oriented communication. This is based on some IP and dynamic data serialization, and some IP already includes serialization on a very high layer so that it can be used also for CAN XL. When we embed Ethernet or IP to a CAN XL frame, all the protocols above those layers can be used more or less as is. Of course, the complexity of the software stack is extended, but basically this is implementation work we have to do, so there are no really semantic changes. For hardware filtering, maybe a node address can be introduced, or we can use the acceptance field to map the MAC or IP address at least partially to the acceptance field. Some CAN seems to be the nice idea that could be possible. So in that way we could save the TCP IP stack, which saves memory, which saves runtime. Early filtering is also possible by making use of the service data type field or the acceptance field. And so, well, I think this shows that the old world is not ready to retire yet. Thanks for your attention.